Hello everybody, my name is Alex Surnov. Welcome to the YouTube channel Numbers, Life and More. Welcome to the course of lectures on mathematics and biology. I remind you that this course aims to provide some overview of just the general structure of mathematics. So it's not a tutorial course, it's rather the course for biologists who want to have an idea of what mathematics studies and how to communicate freely and seamlessly with bioinformaticians, and how to make sure that the bioinformaticians really understands the biological essence of the mutual job. So here is our fourth lecture, and for a better understanding of this, I deeply recommend you to go back to the previous lectures as well. This lecture is titled Differential Equations, and I must say it's a little bit of a tricky topic to discuss, because differential equations appear approximately everywhere on one hand. They are a versatile and common tool for modeling in various aspects of biology, chemistry, physics, any kind of natural sciences. So the sooner I introduce them to you throughout this course, the better it actually is, because this way you will quickly have an idea of how mathematicians model biological processes. On the other hand, there is no unified way to solve an arbitrary differential equation. Most of the solutions are sort of obtained as particular cases, as specific cases. They are not supported or poorly supported by unified umbrella theory. And if there is such an umbrella theory, it is so complicated and relies on so deep mathematical concepts that it makes it impossible to discuss right here at the fourth lecture of our course. So I decided to show you here some examples to give a general overview on differential equations and the models that use them. And all the technical details I will discuss later once we progress through the course. And here is the slide that summarizes this message. I will try to keep the talk concise. However, I realized that it must be split into two parts. There is no way I can fit everything I want to say just in this lecture. So just as an announcement, the lecture 4 will be composed of two parts. One is being currently recorded. Another one will come later and will be announced separately. It's going to be the second part of the lecture 4, also on differential equations. Now, as I said, I will show you valuable examples, and those technical details that govern the theory of differential equations intrinsically will be omitted here, but we will certainly return to them once we learn other aspects of mathematics. Once we learn something like functional calculus, maybe a little bit of probability, we will return back to it. And also, as I said, lots of differential equations don't have some particular ways of solving them. Therefore, numeric solutions using computers are very popular, and they turned out to be pretty powerful as well. Just because researchers don't have any other options, they had to develop powerful computational solutions. And this aspect we also will not touch in the lecture 4. We will rather make a specific lecture fully focusing on computational numeric solutions, because this area is really important for applications and it deserves a separate talk. Okay, so once these comments are clearly said, let's proceed with the actual part 1 of the lecture 4. Here we will talk somewhat about those exact solutions that are known in some particular cases, some methods of solving certain classes of differential equations, and a little bit on some very basic general results that were obtained for differential equations. I recommend you some books. For the beginners, I found this book by Nagy the most appropriate. It's written in a very simple language. It has a lot of examples, and it studies some particular problems that you can use for training, for your personal training. And the good advantage of this book as well is that it is freely distributed as PDF. It's available at the webpage of Michigan State University. Another book which shares most of the same properties, which I found also pretty nice, is this one written by these 3 Russians back in 1985, but obviously the theory hasn't changed much. Like, the basic theory is the same between 2021 and 1985, so you can use this book as well, although it can be difficult to get this book as PDF. At least I couldn't find it. You certainly can buy it in a printed form, but I failed to get a PDF anywhere. I will keep mentioning Andrei Tikhanov again and again throughout this lecture, and maybe in some other lectures, because he was a truly genius researcher, very prominent for multiple deep results in the theory of differential equations. Here are 2 other Russians who completed a great job of assembling known solutions to some specific differential equations in the same book. It is a list of known exact solutions, which is pretty useful actually, because, as I said, it's hard to figure out an exact solution generally. These 2 books are also nice, but they are for advanced readers. I found it so. They rather concentrate on the unified theoretical approaches in these aspects where those exist. And most of the concepts that these books highlight, I need in these lectures, in the lecture 4 specifically, exactly as I mentioned, because they are too advanced for our current backgrounds. We will return to some of them later, but not now. However, if you do want to study the theory deeper, then please pay attention to these 2 texts as well. And also, for some individual slides, I will have additional references which are not included in this global slide, but will be provided as I, start discussing the appropriate topic, the corresponding topic. Alright, so the books are here. Now let's talk about what differential equations actually are. And we will start with some examples. By the way, as in previous lectures, here on the right margin, there is going to be a table of contents growing continuously. So as we discuss a particular topic, it will appear here somewhere. So the examples. Previously, in the lecture 2 and the lecture 3, we have met the equations, which are some mathematical expressions using numbers as input and output. So the expressions linked two parts with the equality sign. It's a certain condition that the members of these equations are subjected to. And the unknowns, as well as the parameters, were numbers, as shown here. This is the polynomial equation of second order with one unknown variable x and three constant parameters a, b, and c capital. Alternatively, here is the set of two linear algebraic equations with two unknown numbers, x and y, and with six constant known parameters a, b, c, d, e, and f. Contrary to this, a differential equation is a sort of equation where the unknown elements of it is a function itself. So the solution to this equation is going to be a function, not a single number. A whole mapping that provides the correspondence for the input argument in the values domain of this mapping, right? So we discussed the concept of functions in the lecture 2. We also discussed the concept of the function derivative, the derivative of a function, also in the lecture 2 and in the lecture 3 as well. And here is one of the examples of a differential equation. It's expression that equalizes the function's derivative with a certain formula that involves the function itself and probably some constant parameters as well. Or here may be x2 in this formula. So what do we have here? We see that df over dx equals to a constant parameter r times f times 1 minus f over k, where k is a constant parameter as well. Another example is the expression that links two derivatives of first order and of second order together with the function itself, and also equalizes it to 0 in this case. Or here can be some other known function of f. Of f or of x. To solve such an equation means to find f as the entire function. And why do these equations appear? Well, because for lots of natural processes, it is either deduced theoretically or measured experimentally that there are mathematical expressions that link the velocity of this process to the state of the process itself. So if f is the, I don't know, size of a population of certain animals or cells or some other proliferating material, so to say, the rate of its proliferation, the velocity of the proliferation, which is denoted as the derivative of this function over time, is linked mathematically to the instant value of this quantity, to this instant value of this variable. If we have f rabbits at point t, they will multiply with the rate df over dt equals to some expression, whatever, g of f, like here, for example. These dependencies reflect the natural behavior of many natural processes. The rate is expressed via the state. Differential equations have a number of properties. I will read these paragraphs to you just now, and then we will go through them one by one in separate slides. First of all, as with integrals, initial conditions or other conditions are needed. Secondly, the good thing is that there is the existence and uniqueness theorem, which demands that the solution exists under pretty general constraints that you put on this equation. And this solution demonstrates some good properties, namely it's continuous with respect to initial values and parameters. That's good news. The bad news is that a general solution method does not exist, as I already said. Some equations do have a closed solution in elementary functions, like sine function, exponential function, whatever. But some others are solved using special functions, the functions formulated via integrals or some other complicated expressions. But majority of the differential equations just don't have a anyhow closed solution, and they are solved numerically or studied qualitatively. Okay, so let's go through these comments one by one. First, as with integrals, initial conditions or other conditions are needed. And here I refer to my lecture 2, where we had the problem of computing the integral of a given function. Let's recall how it was. We had a known function v of x and an unknown function f of x, such that v of x is the derivative of the unknown function f with respect to x. And we had to reconstruct the function f. That's the simplest example of a differential equation. We have an unknown function. We know something about its derivative. Well, namely, we know the derivative itself. And we need to reconstruct the unknown function. And, well, I took this picture from the lecture 2. Briefly, I just mentioned that we discretized x and approximated the derivative with a ratio of finite differences, and then we took a limit of this approximation. It doesn't matter for us right now. The key point is that back then we needed to know an additional condition, namely the value of the function f computed at a given point x sub 1, in order to pick an individual solution to this equation from the infinite variety of possible solutions. So many functions satisfy this equation here, but just one of them satisfies both the equation and the initial condition. And the same thing happens to just arbitrary differential equations. Here is an example of a differential equation. It's a pretty complicated formula. I just intentionally made it such for you to appreciate that the equations can indeed be complicated. And here are the possible solutions to this equation. They all differ. So actually x is on the horizontal axis, f is on the vertical axis, f is the unknown function, and all these solutions differ from each other by their initial condition. F of 0 equals to 1 corresponds to the blue curve, f of 0 equals to 10 corresponds to the brown curve, and all the variety of the solutions between them. Alright, that's important to keep in mind. Now, the existence and uniqueness theorem. That's a pretty useful thing. What essentially it says is that the solution does exist. Usually, this theorem is referred to as the Picard-Lindelof theorem, However, some other researchers did prove specific cases of it even previously, like mentioned here, Lipschitz and Cauchy. I'm not going to tell you right now the exact formulation of this theorem, as well as I'm not going to tell you the proof or even the concept of the proof. We will return to this theorem later when we study the elements of functional calculus, and in particular when we study the so-called Banach fixed point theorem. By the way, Banach is a very prominent and very successful Polish mathematician who contributed considerably to the foundations of mathematics. He proved really deep results that connect different parts of mathematics together in the field of functional calculus. So essentially, okay, what does the existence and uniqueness theorem say to us? Essentially, it says that if there is a differential equation with some very broad constraints on its right-hand part, this function g of f and x, then the solution does exist. And if additionally an initial condition is specified, then this solution is unique, as shown here. The initial condition is marked with this orange dot, and then the solution does exist, a unique solution does exist. It may exist not over the entire range of x, but it certainly does exist over some ranges of x, which are denoted here as epsilon. Once x propagates outside the epsilon region, the solution may disappear. The theorem doesn't say anything about the long-term behavior of the solution. But within epsilon, the solution does exist, and once the initial condition is provided, it's unique. Once again, there are constraints, there are conditions to this theorem. It doesn't hold absolutely all the time, but it holds for the majority of practically valuable examples. Let's put it this way. Now, this solution also has a number of good properties. This solution also has a number of good properties. Again, not absolutely in every case, but in a general position, so to say. These properties are the following. The solution being evaluated at a certain point x not equal to 0 continuously depends on the initial condition, the value of the solution at 0, and on the constant parameters within the equation. So here is the equation that was there 2 slides ago, just with 1/2 here being substituted with the fixed parameter k. And well, let's keep k equal to 1/2 for now, and let's consider this picture in the left of the slide. We have a family of these solutions to this equation which differ from each other by their initial conditions. The initial condition f of 0 varies from 0.96 to 1.05. And then the solution is evaluated over a short range of x, specifically at the points x equals 1, and the value of f of 1 is plotted against the value of f of 0, the initial condition. And we see that this dependence is linear in this case. It's continuous, first of all. In this particular case, it's also linear, but it doesn't have to be linear. The most important thing is that it's continuous. And that's good. It means that by modifying a little bit the initial condition, we likely can expect that the value of the solution somewhere close to the origin will still vary a little. By varying the initial condition a little, we sort of impose that the final state will also vary just a little. Of course, later the trajectories may diverge, but at a short region they stay close to each other. The same thing happens with varying constant parameters of the equation. So here we keep the initial condition fixed at f of 0 equals to 1, but we start ranging k. We start varying k, and we plot the value f of 10 against k, and we see that the dependence is still continuous. It's not linear anymore, but it's a smooth curve, with some bumps. It asymptotically goes to 0 here and asymptotically goes to infinity here, but still it works. It's continuous. It's good. It gives us certainty. It gives us some confidence that by changing constant parameters of the equation, we don't accidentally catapult the solution somehow outrageously. Once again, it doesn't hold all the time. There are some exceptions, there are some conditions when irregularity may happen, but in general position it does hold, okay? On this, the good news are over for a moment. Let's examine some sad properties of this whole topic. A general solution method does not exist, meaning that there is no algorithm that allows you to solve an arbitrary equation. For some equations, a closed solution in elementary functions is available. Like, for example, this equation here. The second derivative of f with respect to x minus k times f of x itself equals to 0. Here k is a positive constant. This solution does this equation does have this solution written at the bottom, somewhere quite close to the subscribe button of this YouTube channel, and quite close to a like button, by the way. I mean, I hope I drove your attention to these two buttons. This solution has the following shape. It's c1 times e to the power negative square root of k times x plus c2 times c to the power square root of k times x, where c1 and c2 are constant, just constant numbers. Notice, please, that this equation has two derivatives. It has a second order derivative, and therefore we end up having two constants in the solution. So we need two initial conditions. For example, it may be the value of f at 0 and the value of f prime of 0, the derivative of f at the point 0. It's intuitively understandable that the higher order differential equation results in having more constants in the end and results in requiring more initial conditions, because we kind of have to integrate the expression twice. First to get rid of the first derivative and then to get rid of the second derivative as well. So this kind of highlights or intuitively indicates why we need the two constants and two initial conditions. But what I want to say right here is that even under a minor modification, this equation may not have a closed elementary solution anymore. So for example, if we substitute k with x, with the independent variable itself, then there is no such simple formula. And most of the textbooks recommend to search the solution in the form of a series. A series, I remind you, is a sum of the infinite number of summands, as shown here. A sum over n, with n ranging from 0 to positive infinity. And in particularly this case, the series is a so-called power series. It contains a constant parameter in every summand and a certain power of x. And then one can figure out what these parameters should be. That's, by the way, is called ARY, the ARY equation. AIRY, if I'm not mistaken. And it appeared first in the studies of astronomical observations. And as I said, an arbitrary differential equation likely must be solved numerically, because even this form may not be a solution anymore, this expression or expression of this kind. Okay, so these are the 4 comments. Now let's go over some particular examples of differential equations. How do they look like? How to solve them? In which cases they can be solved? What is just known about it? Without going too crazy, without going into too much of depth, you know. Linear differential equations of first order. The first order means that there is only the first order derivative is there in the equation. Linear means that the right hand part is linear with respect to the unknown function, meaning that x itself may contribute somehow non-linearly, but f is positioned there only as a multiplier with no powers, with no other complicated functions. So here is the full problem with the equation itself and with the initial condition. A is the original value of x, b is the original value of f, f is the unknown function. And let's examine first the very simple particular case of this equation, where h of x is equal to 0 and g of x is just constant. It's the constant value, constant parameter r, and f of 0 is b, so a is equal to 0. What can we do? We can do an informal trick which works just because you can substitute the resulting solution into the original equation and make sure that it works. That's it. But the informal rule of solving such an equation is the following. We kind of divide both parts of the equation by f and multiply by dx. Previously in the lecture 2 I specifically said that df over dx is not a ratio itself, it's just a symbol. But in this case, informally speaking, we can do such an operation and obtain this expression from the top equation here. Then we have to subject both parts of the equations to integration in order to get rid of these derivatives of the differentials. Okay, let's formally write the integration sign and think for a while which ranges of integration should we use. Well, apparently, as we can show post factum, these ranges can be used. X ranging from 0 to c, where c is the arbitrary point at which we want to evaluate the function f, and f of x ranges from b, which is the initial condition, to the value f of c. This is a number. This is just a certain number that we don't know yet. We know C, or we specified C arbitrarily. We don't know f of C, but we write it as the upper limits of integration, and we have to find f of C from this expression. So we integrate this and we integrate this, and we eventually obtain this expression here, from which we can express f of C further and conclude that f of C equals to b times e to the power rc. B is the initial value of f, r is the constant parameter of the equation, C is the point of x at which the value of f is evaluated. So essentially, C is just x. F of C equals to this. Once again, this looks like hand waving, and this looks too informal. However, I'm not saying that this approach is strictly proven so far. For us, it is sufficient to be able to substitute this formula into the original equation and make sure that this equation does hold. In the end, it doesn't quite matter how we figured out the formula in the end. We somehow obtained it. I don't know, maybe we just by pure chance imagined this formula and accidentally it works. Who knows? And then once we substituted it into the original equation, we proved that this formula is indeed a solution. And from the existence and uniqueness theorem, we know that there are no other solutions that satisfy the same initial condition. Now let's talk about some more general linear differential equations of first order. First, let's, well, first of all, let's change the notations somehow. Usually, all the differential equations are written for the variables that evolve over time. Therefore, the independent variable, instead of being called x, is more convenient to call t for time. And the dependent variable, the unknown function I mean, is usually called x in this situation. So x of t is the unknown function, t is the independent variable, and let's examine this equation here, where the constant parameter r is now substituted with an arbitrary function g of t. And by using just the same procedures as in the previous slide, we obtain this expression here. That's the solution. Now, what should we do if there is an additional summand in the right-hand part? A summand that is dependent on t as well. Well, it turns out that a similar formula still holds, but instead of having x of 0 as a multiplier to the exponent, we have to substitute here a variable factor, a variable multiplier. This method is called the integrating factor method, and it is explained in the book by Nagy and in the book by Tikhanov and co-authors and stuff. After doing some pretty simple arithmetics, one can figure out in this case that the variable multiplier to the exponent has the following shape. It's again x0 plus a certain integral that looks like this. And this is the solution. That's it. That's the entire solution of the given equation. Linear differential equations of second order. here is the general shape of it. It has the second derivative of the unknown function, the first derivative of the unknown function multiplied with a certain coefficient, the unknown function itself, and this all equals to 0. Well, this equation can be complicated. It can be upgraded somehow. So first of all, these coefficients may depend on t itself. It's important that they don't depend on x, because then the equation stops being linear. But they can depend on t. There can be some free term that doesn't depend on x, which depends only on t here instead of 0. But let's concentrate on the linear differential equation of second order with constant coefficients and with the 0 free term as shown here. And notice that now we have two initial conditions, x of 0 and x prime of 0 are given. What is this equation? What physical process can it describe? Well, it can describe the motion of a pendulum. According to Newton's second law, here is the balance of forces. We have the acceleration term. Mass times acceleration is the force, according to the Newton's second law. We have the term that corresponds to friction, and it's proportional to the velocity. The higher the velocity, the more friction there is. And we have the term that is proportional to the position of the pendulum itself. And by x, I mean the horizontal coordinates of the weight of the pendulum, of its endpoint. This term represents the external force field. It represents actually the gravity, the effect of gravity. In fact, it's just working approximately, because the correct formula for the gravity effect involves different sine functions. It involves the projection of the point's position onto one of the axes. But when the deviation of the pendulum is small, the deviation from the equilibrium, then the sine function can be approximated with x itself, as shown here. So the black line here is the sine function, the red dashed line is x, and we see that for small deviations they almost coincide. So this equation here describes the physical reality fairly well. And also I wanted to give you some common notations. In case of the time dependence, the derivative over t quite often is notated as x dot instead of x prime, and the second derivative is x double dot also instead of this. But I will stay stuck to the previous notations just to avoid overcomplicating the writings. Just be aware that you can find such notations in books somewhere. Okay, so how do we solve this equation? We will search the solution as an exponential function. We hypothesize that e to the power rt, where r is an unknown constant, satisfies this equation. And we substitute it into the equation, we do some arithmetics, and we figure out that r, in this case, must satisfy this second order polynomial equation, and we know the solution to this equation. We know the formula for the roots of this equation, and here it is. Two values of r correspond to this equation, they satisfy this equation, r sub 1 and r sub 2, and they differ by the sign of the square root here. And that's a powerful result. It can be fully appreciated when accompanied by the following theorem. The theorem says that for an equation of this kind, if you find two linearly independent solutions, two solutions that are not proportional to each other, then an arbitrary solution of this equation is just their weighted sum. So from knowing two solutions, you can reconstruct any solution just by varying the weights that you multiply them with. And now let's have a look at the behavior of this solution. And by the way, what I just said is written here in words. A general solution is just the weighted sum of the two particular solutions, where C1 and C2 are the weights, and they are computed from the initial conditions. So let's now take a look at how these exponents behave. The first case is when both values of r are real, r sub 1 and r sub 2 are real. Then they can be either negative or positive. And therefore, the exponents can either diverge or either converge when r is negative or diverge when r is positive. For example, like here, the particular solution that corresponds to the negative r converges to 0, as shown in the green line. The particular solution that corresponds to the positive r is the blue line, and it is diverging, it grows unboundedly, and their sum is diverging too. Alternatively, both r's can be negative, and their sum is converging as well. Another case is when both r's are complex. Actually, there cannot be a case when one r is real, another one is complex. That's forbidden. It follows just from this formula here, obviously. So if the expression here in the square root is negative, then both r sub 1 and r sub 2 are complex, and they are the complex conjugate of each other. They differ from each other just by the sign of their imaginary part. And therefore, we can represent them in this form. Both r's are equal to some p plus I times s, or minus I times s. And both p and s are real numbers, as I told you in the lecture 3. And as I told you in the lecture 3 as well, this expression can be reformulated in terms of the Euler's formula, where the real part goes into the exponent, and the imaginary part is decomposed into the sum of trigonometric functions. So from this formula, it is seen that the behavior of the exponents is oscillatory, and the amplitude is dictated by this factor before the parentheses. So given that p can be either negative or positive as well, these oscillations can either vanish in amplitude or unboundedly grow in amplitude, like shown here. Notice, please, that we assume the initial conditions real, with no imaginary part. The coefficients here, a, b, well, a and b, are also real. We assume them real. And therefore, even though the general solution does have an imaginary part, there is no way the imaginary part may appear in the particular solution that satisfies these equations. Because these numbers are real, these numbers are real, all the i's must cancel each other when the constants C1 and C2 are computed. And the final answer, the solution to this equation that satisfies to these initial conditions, will also have only real values, as shown here. In case of the negative p, it is a vanishing oscillation. In case of the positive p, in case of a positive p, it is also an oscillation that grows, and the amplitude grows exponentially with acceleration. The second-order linear differential equations are tightly connected to the sets of first-order linear differential equations. For example, consider this set where x and y are both the unknown functions of t, and p and q and r and s are the constant parameters. Then, by expressing y from x, we can convert the system into a linear second-order differential equation with respect to x. And the initial conditions that we supply to this equation can also be converted into the initial conditions with respect to x of 0 and x prime of 0. And then we can study this equation, this system, using the tools that we just developed for this second-order linear differential equation. What can I also say? Sometimes the equations may involve some upgrades. They may involve inducing term here, which depends on t. It's like an external oscillatory force or external force of another kind. They may have degenerate roots of the polynomial equation with respect to r, which I just showed to you. So they can be just 1r, like in case of r squared equals to 0, for example, right? 0 is the only root of this equation. It's a degenerate one. For these cases, the behavior of the equation is also studied, and there are formulas to apply. But of course, as the equation gets upgraded more and more, the chance that an appropriate formula exists becomes smaller and smaller. And the example is the Airy equation that I showed you a couple slides ago. But for this case, the behavior of the linear system of two equations can be effectively studied through the behavior of the second-order differential equation. And how do they behave? Well, if both roots of the polynomial equation, both values of r are complex, then both x and y evolve in an oscillatory manner, and in the coordinates x, y, the system just either approaches the origin by spiraling around it, or it flies away from the origin, also according to this, along this spiral trajectory. The direction of motion is dictated only by the sign of the real part of r. And here is the dependence of x and y on time. So time is propagating rightwards, and this is the shape of x of t and y of t. Alternatively, both values of r can be real, and then the solution can either converge to 0 in x and y coordinates. The system starts in the original point and then just somehow evolves and then falls into 0. And that's how it looks in the t dimension. Or it can symmetrically diverge from the origin somewhere to the infinity. Alternatively, the system can diverge differently in different directions. So like here, it starts from the initial points here, somehow moves, and then approaches another asymptotic line and goes to infinity along this line, or approaches this line asymptotically. If we propagate this solution backwards in time, it will approach another asymptotic line and go to the other side of infinity. And here is the time dependence of both the components of the solution, x of t and y of t. So it's a pretty variable behavior, but it's fully classified in case of a two-dimensional system with constant parameters. And we will use this for studying approximately some more complicated equations, nonlinear equations. But we will do it in the second part of this lecture, which will be published separately and will be announced separately. A logical continuation of the former topic is the set of the arbitrary number of linear first-order differential equations. So here we have n unknown functions, x sub 1, x sub 2, x sub n, and they all are related to each other with a linear combination, with a weighted sum with certain weights. There is a method to study this system as well. The method is explained in Nagy section 5.1, in Morris and Tenenbaum lesson 31D. This method involves computing the eigenvalues of the matrix of coefficients, the matrix A in this case. So all these A sub 1.1s, A sub 1, 2, etc., they are the elements of the matrix A capital. We can compute the eigenvalues of this matrix, and from them we can express the solution via some arithmetics which is bulky, but it's not hard. It's just, I don't want to waste time explaining it right now, but there is nothing very complicated. The complicated part is actually to find the eigenvalues. And by the way, for those who forgot what eigenvalues are, I refer to the lecture number 3. I explained it there. So as you remember from the lecture 3, this equation which the eigenvalues are found from, the eigenvalues lambda, is a polynomial equation of nth order. So there is no a solution to this equation in elementary functions in general case. Therefore, these lambdas have to be found somehow separately using a computer, using some approximations, and then from them the solution to the equation will be reconstructed. Some upgrades to these systems are also allowed when the roots are degenerate, when maybe some dependence on t is allowed, but again, the more you upgrade the system, the less there is a chance that the closed solution in elementary function exists. Okay, that's it with linear differential equations. Let's proceed with nonlinear ones, and on this we probably will finish. But we're not finishing the current talk yet. We're just moving to another part of it. What would you think it is? That's nonlinear differential equations. There is one example of a nonlinear differential equations that has a particular connection to biology. That's the equation of limited growth. And I showed you already this equation in the very beginning as one of the first examples of differential equations as such. Here it is. Dx over dt equals to constant r times x times 1 minus x over k. It's also known as Verhulst equation. Verhulst is the researcher from Belgium who lived in the 19th century. And essentially he was unhappy with the equation of unlimited growth, which we already studied, which leads to an exponential growth of the population. And he was unhappy with this equation for a reason, because this equation doesn't explain when the growth is saturated, when the population reaches its boundary. It's maximal possible size. And Verhulst proposed the term that describes the competition between the members of the population. So in addition to this constant factor r, the equation also has the factor that linearly decreases as x grows. 1 minus x over k, which means if we open these parentheses, the equation will state that dx over dt equals rx minus r over k x squared, meaning that the rates of growth decreases proportionally to the square of the population size, meaning that once two members of the population meet, they start competing with each other and don't let each other to grow, don't let each other to multiply. The number of possible meeting combinations is actually proportional to x squared, because every member of the population can meet every other member of the population. So how can we solve this equation? We again apply the same trick as for the unlimited growth case. We divide both sides with the right hand part and we multiply with dt. And then we have to integrate this expression. This looks like a tedious task, but smart people learned how to do it. I definitely refer you all to this textbook of calculus by Courant and John, which I already mentioned in the lecture 2, and specifically to the section 3.12 of it, which is titled Integration of Rational Functions. So this is a fraction. This is a ratio, which we have to integrate. And there is a trick. Every ratio of this kind can be represented as a sum of elementary ratios, like here, with some unknown factors a and b, unknown so far. But we can figure out what a and b are by actually equalizing them to the corresponding parts of the numerator in the left hand part. So we know that 1 over this expression must be equal to this sum of a over x and b over 1 minus x over k. We compute this sum, we compute the numerator of this sum. The numerator is this, and then we just claim that the fragments of this numerator that has no x must be equal to 1. Here is the 1. And the fragments of this numerator that is proportional to x must be equal to 0, because in the left hand part there is no fragment that is proportional to x. So by realizing this constraint on a and b, we can immediately evaluate A and B strictly. We can therefore represent the original quadratic ratio as the sum of the first order ratios, and the integral of the first order ratios we know. It's written in the list of integrals in every calculus textbook. So this equation here turns into this equation here, and then once these two guys are integrated, x of t can be reconstructed by just using some elementary arithmetics, and the behavior of this curve is just the same as Verhulst intuitively proposed. It grows more or less exponentially while the competition term is close to 1. But then, once the competition term grows as well, or vanishes as well, I should say, the velocity decays and the function plateaus. So here is the x of t in linear scale, here is x of t in log scale. We see that it's asymptotically exponential in the beginning and then just goes to a plateau. That's the equation of limited growth. Another valuable model is the model of chemical kinetics. It's trickier. This slide is busy, it contains many formulas, but we will need to go through them because they contain a few really valuable hints for studying differential equations further in general. So let's consider this chemical reaction of the components A and B. A plus B converts to C with the reaction rate K, or the reaction constant K. According to the law of mass action, the derivative of C equals to the product of K, A, and B, where C, A, and B are the concentrations of the corresponding components. So what can we do with this? We can, first of all, we notice that the derivative of A and the derivative of B is just the same as derivative of C with another sign, because the velocity of accumulation of C is just the same as the velocity of the degradation of A and B, or the velocity of disappearance of A and B. Okay, once we wrote this set of equations here, we can, first of all, we see that these equations are nonlinear anymore, so we cannot apply these rules for linear equations that we just discussed, but we can derive A from the second equation, from B. We can divide everything by B, and B is non-zero, which makes the operation valid. And then we obtain this expression dB over B dt. Let's notice that this is just the same as the derivative of logarithm of B. Why do I claim it's the same? It's the same according to the table of derivatives that I presented in the lecture 2. Please refer to this, go to the lecture 2, open the table of derivatives, and compare the derivative of the composition of two functions, the derivative of f of g of x with respect to x, with the derivative of the logarithm function. And you will see that indeed dB over b dt is just the same as d logarithm b over dt. Okay, so now we expressed A via B, and I marked it with the exclamation points here because it's a valuable trick. It's useful to remember that these two expressions are the same. Now, we substitute the expression for A into the first equation, and we close this expression, this first equation, with respect to B only. It's the second order derivative of B. Let's call logarithm of B as another unknown function x, because only the logarithm of B, well, not only, but it's just simpler to call it x, and we call B as e to the power x. The expression gets seemingly simplified. What do we see here? Here another useful trick comes in play, and I also want you to appreciate it. If we have the second order differential equation which includes only the unknown function but not the independent variable t, we can denote the derivative of the unknown function as a new unknown function of the x itself. So we had the equation with formulated for the x of t. Now we formulate an alternative equation, or how to say it, a modified equation, derive an equation from here for the y of x, where x is now the independent variable. So long story short, we call y of x, we call it the dx over dt as y of x. We substitute this expression into the original equation. We notice that the second derivative of x, according to the same table of derivatives that I just mentioned, equals to dy over dt times y. That's another useful trick, and I want you to think through it. And then by substituting y into the original equation, we simplify it. We obtain a first order differential equation with respect to y. From having the second order differential equation, which does not depend on the independent variable t, we now obtained the first order differential equation with respect to y, which, although does contain the now independent variable x. Here is the equation. This one is equivalent to this one. And this equation can be solved just, well, you know, we integrate it once, we obtain this value for y, this formula for y. The first integration constant appears. We will have to figure it out through the initial conditions. We now recall that y of x is dx over dt, and we derive from this equation that dx over dt equals to negative k times e to the power x plus c1. And we integrate this equation too, just the same as we did with the limited growth equation. We divide both parts of the equation by the right-hand part and multiply by dt. We integrate, and we find out that x, which is the logarithm of b, and t, which is the original unknown variable, are linked together with this algebraic formula. It involves t, x itself, and certain logarithms, yeah, this expression of this kind. And sadly, that's it. We can't move any further. That's the terminal station. The train is not going to go longer. Please, ladies and gentlemen, leave the compartments. From this algebraic equation, x, unfortunately, cannot be reconstructed in a closed form using just elementary functions. This algebraic equation doesn't have an doesn't have a closed solution. It still means that there is the function x of t, and therefore there is a function logarithm b of t and b of t. That's for sure. Just this function is inexpressible in the combination of pluses, minuses, exponents, sine functions and stuff. Just there is not such a formula. The function exists, but the formula doesn't exist. And it's sad, but this happens. That happens quite often. This is the illustration that even simple equations may not really have closed solutions. But still, I find it valuable to discuss this example with you, this problem with you, because first of all, it contains two valuable tricks. The trick of using the logarithmic derivative and the trick of substituting dx over dt with y of x. It's important and useful to remember. And also because this is already a great simplification of the original system, honestly speaking. By studying carefully this algebraic equation of x that links x and t, one can better understand the relation between x and t, the asymptotic behavior of it, and one can really say quite much about the behavior of the original system, especially if such a situation appears not for a simple system like this, but for some more complicated set of equations, more complicated chemical behavior, whatever. So simplifying the original differential equation to an algebraic equation is already a great deal. I mean, for complicated systems, one can defend a thesis on this, really. But the behavior of this chemical system can be easily computed numerically, which I did here, and one doesn't need analytical expressions for this. One just needs a powerful computer that quickly evaluates all this kinetics. So that's it about chemical kinetics. That's it about solution methods. Now we're gonna say just a few concluding remarks and examine a little bit more of physical and biological examples. If the law of mass action is taken to its extreme, one can construct the so-called coagulation equation. This equation is dated back to the works by Marian Smoluchowski, who was a Polish physicist who committed a great contribution to the theory of diffusion and the theory of stochastic processes, who communicated to Albert Einstein a lot about these subjects. And essentially, he studied the hierarchical aggregation of monomers in a certain medium. So here we have two monomers. They can collide to each other and form a 2 cluster. A 2 cluster can collide with another monomer and form a 3 cluster. Two individual 2 clusters can collide together and form a 4 cluster, and so on. And every interaction here can be treated as a chemical reaction, with the two contributing subclusters being interpreted as the reagents, and the resulting cluster interpreted as a product of the reaction. Every such reaction can have its own value for the velocity constant. In the previous example with A plus B turning to C, we had just one constant, K. But in this case, every type of clustering can have its own velocity constant, depending on the size of the reagents. And when we account everything carefully, we can obtain the equation written down here. What does it say? Well, it operates the values n sub I, which is the number of the clusters of the size I. Here the I is just the index, by the way. It's not the imaginary units. There are no complex numbers here. Everything is real. So n sub I is just the number of clusters of the size I. And that's a function of t. And the kinetics of n sub I is the following. It has the influx, which is provided by the collision of the two subclusters that can form the I cluster upon aggregation, namely a J cluster and a I minus J cluster. So they collide to each other, they are multiplied by a certain velocity constant, and all these influx terms are summed together, divided by 2 because it must be symmetric with respect to the permutation between J and I minus J. The collision of I minus J cluster and the J cluster is just the same as the collision of a J cluster and the I minus J cluster. And also this value here has the outflux, which is provided by the interactions in which the I cluster is playing the role of the reagent itself. So the I cluster can meet a J cluster and form the I plus J cluster. So this is probably the most of what one can do with the law of mass action. The most complicated system. Well, one can introduce some dissociation of clusters as well, but it doesn't change the picture qualitatively. And the question is, does this equation really have physical sense? And the answer is yes and no. In the form which is written here, the equation does have a perfect physical sense. But there is a caveat. This equation assumes that the clustering can propagate infinitely. Here we assume that for every two cluster sizes, there is a way to interact and there is a way to produce a yet bigger cluster. One can ask how then it coexists with the law of mass conservation, and the answer is that the functions n sub I of t are not integer. Heavier and heavier clusters may form in quantities which are smaller than 1 in the formalism of this equation. So the equation is constructed based on the law of mass action. It means that it is constructed for continuous functions, not for discrete functions, with respect to t, I mean. And it means that it must operate the sizes of clusters, which can take values of 0.1 or 0.01 and so on. And once these clusters aggregate further and further, the number of heavier clusters will tend to 0, although remaining positive. And well, some physicists may be unhappy with this. If you really want to concentrate on the discrete sizes of discrete number of clusters, you indeed may not be happy with such an approach. You don't want to see that the number of clusters of size I equals to 0.01 or whatever. Can we then maybe truncate these sums? Can we put here another constant value instead of the positive infinity? Maybe if we just truncate the summation at a certain level, the equation will liberate ourselves from this strange artifactual effect. And the answer is no, not again. Let me show you how the kinetics works in this case. Here is the equation where the total mass originally is equal to 10 and the velocity constant is formulated as follows. It is 1, just a constant, when the two interacting clusters in total give you less mass than the total mass, and 0 otherwise. This condition prevents the heavier clusters to appear. This condition prevents the clusters with the mass larger than the total mass appear. How does the function behave now? How does the equation behave now? The good thing is that this equation now does satisfy the law of mass conservation. The total mass in the system stays always equal to 10. However, the bad news is that still the number of clusters doesn't end up being integer. In the beginning, so let's take a look at the axis labels here of this heat map. Time propagates from left to right, and the cluster sizes are stacked one above each other. And the colors of the heat map represents the mass sequestered or contained in the population of clusters with the given size. So in the beginning, the entire mass is concentrated in the clusters of size 1, essentially the monomers. Then, pretty soon, the clusters of size 2 appear and they take some mass from the monomers. And further, the clustering propagates until at some point the majority of mass is concentrated in the cluster of size 10. However, we can notice here that the mass concentrated in the clusters of size 10 is not 10 itself. It's not the total mass, meaning that there is less than one cluster of size 10 in the system according to this equation. Again, the count of clusters is continuous. It doesn't have to be integer. And in this case, even the steady condition of the system suggests a non-integer count of the most heavy cluster and other clusters as well. So this example shows you that not for every case you can formulate a mathematical model naively. Even though the coagulation equation is widely used, it still exhibits a lot of hidden obstacles and underwater rocks. And, well, yeah, that's just how life is. You cannot put together mathematical formulae and expect that they will work by default. You need to carefully keep track of whether this equation indeed makes physical sense or biological sense. Once again, why this happens with the coagulation equation is more or less understandable. Once the clusters stop being numerous, the statistical laws that compose the basis for the law of mass action stop holding. You cannot just think statistically of individual clusters, or you cannot think statistically of the situation where the counts of clusters is very small. And since you cannot think statistically about this situation, you cannot use the law of mass action either. So just keep this in mind. It's rather a bizarre thing. I'm pretty sure you're not gonna face it regularly, but who knows? Look, biology is a complicated science. Processes in biology are very convoluted and unobvious. At some point, your bioinformatics colleagues may come up with a proposal of using the coagulation equation in describing some of the processes, and then you must say, well, let's sit together carefully and go step by step through your formalism, just to make sure that we don't end up in a misleading situation of this kind. Okay, I think I said everything I wanted about the coagulation equation. Let's say a couple of words about the differential equations that involve partial derivatives. As I mentioned in the lecture number 3, if there is a function that depends on several independent variables, as in this case x1 all the way to x sub n, it can be differentiated separately with respect to each of the arguments. And this operation is called partial differentiation and partial derivative, and that's how they are denoted with this round differentiation signs. And the first order partial differential equation is essentially a formula which links together the values of the first derivatives of the unknown function itself maybe, and the independent variables maybe. These equations can be converted into a set of ordinary differential equations. The equations with just one independent variable and with regular derivatives, not partial derivatives. Here I refer you to this Wikipedia article. It's quite well written, and also it refers further to this textbook by Andrew Forsyth. So essentially the first order partial differential equations are not much different from ordinary differential equations, the same thing. However, the situation changes when we come to second order partial differential equations. A second order partial differential equation is a similar formula which includes, in addition to all the previous terms, also the second derivatives. And these can be the derivatives with respect to the same variable, or these can be second derivatives with respect to different arguments, different variables. Which books can I recommend for investigating this theory further? There are two books. This one is freely available. This one can be found freely as well. And by the way, this A.N. Tikhonov is just the same Tikhonov whom I mentioned previously in the beginning of the lecture, just spelled differently, because the endogenous Russian alphabet, the Cyrillic alphabet, apparently allows multiple alternative representations with English letters. Well, the science behind the second-order partial differential equations, it's yet more complicated than the science of ordinary differential equations. But there is still something simple one can indeed say about it. First of all, let's introduce some notations. I realize that you may be already fed up with notations, but what can I do? Mathematicians also are live human beings. I'm sorry, but some of them are more attached to certain notations and some others are attached to other ways of writing. So, in one word, you may find this operation nabla, which is a vector operator. It's a little machine to which you can feed a certain argument and it will return a vector. So if you feed to it a function that depends on several arguments, x sub 1 all the way to x sub n, then the operation nabla returns the so-called gradient of f. I also mentioned the concept of gradients in the lecture 3. And essentially, in Cartesian coordinates, the gradient of the function f is the vector whose elements are the partial derivatives of the function f with respect to the corresponding coordinates. You also can apply the operation nabla to a vector field, which depends on the same coordinates, the same Cartesian variables. And then the action of the nabla operation on the vector fields is treated as a dot product, which I previously denoted in the lecture 3 as this like writing, and which is also denoted sometimes with a dot. And according to the regular formula of the Cartesian dot product, the output of the nabla operation when this operation is applied to a vector field is just the sum of the first derivatives of the corresponding elements of the vector field with respect to the given coordinates. Also, for shortness, for brevity, usually the derivatives with respect to certain coordinates are denoted as a sub-index for a function. So if there is a function u that depends on t and x, the derivative of u with respect to t is denoted as u sub t, and the derivative of u with respect to x is denoted as u sub x. Being informed about these notations, we can examine the two mostly commonly used types of the second-order partial differential equations. One is the hyperbolic equation, and it's called the wave equation as well. And another one is the parabolic equation. And this parabolic equation describes the diffusion of chemical compounds or diffusion of heat in a certain medium. So the wave equation seldomly is used in biology. I don't see very often this equation in biological papers. But the heat equation is used quite massively. Various methods have been involved. A wave propagation method for the wave equation, separation of variables for both of them, Green's functions method for both of them, Fourier transform, I don't think we need to really go into these methods. You can find them in two of the books that I previously suggested. I think we will touch only the Fourier transform method, but not in this lecture, and not even in the next lecture. For now, let's just appreciate that this equation here describes the propagation of a wave through time, which is denoted as t, in the media with the spatial coordinate x. So x is space, t is time, f is the well, the profile of the wave, the deviation of the surface of liquids, or the deviation of the shape of an elastic rod from the equilibrium. And this profile is propagated with respect to this equation where c squared, where c is the velocity of this wave. Alternatively, the diffusion equation tells you how a droplet of a diffusing material, diffusing liquids, let's say, spreads into a medium. If you drop some ink in water, the concentration of ink will follow this equation where A is the diffusion coefficient and is also positive. Heat diffuses the same thing, the same way as well. So why I'm introducing this equation specifically? Because there is a very beautiful application of it, which we'll just discuss a little bit right now. It's called Turing equations, and they are named after their discoverer or their inventor, Alan Turing. It's the same Alan Turing who pioneered computer science, a brilliant British mathematician, and he considers the diffusion of two chemicals, the activator and the inhibitor. They both can interact with each other. They both have some sources and some sinks in the media in which they are diffusing, and they both have the diffusion term. And Alan Turing proved that for some reaction terms P and Q, the uniform distribution of both F and G is not stable anymore. If there was no interaction and no sinks, and well, actually sinks are irrelevant for this case, but if there was no interaction, the uniform distribution between the, how to say it, between the boundaries of the region in which the diffusion comes, in which the diffusion takes place, would be the stable solution. Obviously, if you drop ink into water, eventually it will distribute itself uniformly. However, if there is a set of two equations, if there are two types of ink interacting with each other, they can surprisingly start forming patterns. And here the fact that the system is open is crucial. Components must inflow into the system, and they must also be able to leave the system. The system must be open. So then this uniform situation disappears spontaneously, and the concentration forms such strange periodic or quasi-periodic patterns, well, periodic patterns in the case of Turing's study. And this way, they describe the formation of various patterns in biology. For example, this way they describe the formation of the spots on leopard's hide. pretty beautiful and very much applied. So for further studying, I recommend you again these two Wikipedia articles, and there is a link to the original paper by Alan Turing in this article. Also, there is a good review recently published here in Tübingen, I think, in Germany, that just gives an overview of pattern formation and the usage of Turing equations in biology. This group by Martin Meyer Herman has used second-order partial differential equations for describing tumor progression, or at least tumor tissue growth, sometimes in culture. Also quite useful, and well, as I just said, there are no general methods for solving ordinary differential equations, and for sure there are no general methods for solving partial differential equations, which are yet harder, which are yet more complicated. However, there are some qualitative methods to study partial differential equations of second order, and this heat and mass transfer, heat and diffusion. The advantage of using qualitative approaches is that you sometimes are flexible in choosing these interaction terms. You don't have to specify them exactly, but you can just specify some general properties of them. Let's say P vanishes as f and g tends to infinity, and Q, I don't know, plateaus in the same condition, or something like this. So by sometimes specifying just these general requirements to f and to P and Q is sufficient to derive some qualitative estimates and qualitative conclusions, and such a theory is quite rigorously described in this book, Danilov, Maslov, and Volosov. I don't think it can be found in a PDF format, but it certainly can be purchased printed. Okay, the last thing I wanted to discuss today is some comments and some hints about the general theorem. Indeed, there are methods designed for a broad spectrum of differential equations. There are methods designed for the variety of seemingly unconnected, seemingly dissimilar equations. However, those methods are extremely complicated, and quite often even they don't give you exact solutions. Rather, they tell something about the equation's behavior, the symmetries between the arguments of this equation, and so on. But nonetheless, there is a huge mathematics behind it, huge science. Such concepts as Lie groups and differential forms are used for classifying differential equations, for proving which differential equations have stationary solutions, which ones are, which ones do not converge to any stationary solution, and so on. Prominent names in these fields are Henri Poincaré, Sophus Lie, and Vladimir Arnold. They are the major contributors who established the theory of differential equation classification. And finally, I wanted to quickly mention a very beautiful result, which has tremendous application in physics, is Emmy Noether's theorem. Emmy Noether was a brilliant German mathematician, and she proved a fundamental result which in a way explains how the laws of conservation work, how the law of energy conservation works, and how the law of angular momentum conservation works. Usually we accept those laws just as given. We somehow believe that all the processes in the world simply happen in such a way that the total energy of the system is conserved. But is there a mechanistic reason for it? And a main author proved that the conservation laws originate from the symmetries that the equations governing these processes have. For example, there is this symmetry with respect to moving from one point to another. If you conduct a certain physical experiment here on this desk, and then move a couple meters away and conduct the same experiment there, the result will not change. The properties of the physical system will remain the same. If you turn your system by a certain angle, clockwise or counterclockwise, it also will not affect the result of the experiment, and so on. So some symmetries are there. And the existence of these symmetries, the symmetry with respect to shifts in time, if you do an experiment today, today or yesterday, let's say, shouldn't matter, right? So these symmetries mathematically imply, in a surprising manner, the existence of conserved quantities, conserved features of the system. And that's a brilliant result. On this, I guess I will call it over for today. We did a great job. We still have one more lecture on differential equations, in which we will discuss the qualitative approaches for studying differential equations, because most of the biological equations are too complicated to be studied explicitly, to be solved explicitly. And this lecture will be announced shortly, or at least quite soon, in the ranges of maybe, I don't know, a week or maybe two. Thank you for being with me. Let's stay in touch. Please subscribe, please like the video, please share it, please contribute for spreading it around. Take care. See you next time.